A phase line is a qualitative tool that can be used to study solutions of only autonomous differential equations. True. And what was autonomous again? Governs itself. What does that mean in terms of? It's independent of t. Yeah, the right side only has y's in it, or whatever the independent variable is. I'm sorry, the dependent variable. Okay, classify this equilibrium point. The dot, yeah, what is it? The sink. Everything's going towards it. That's called the sink. And if you're going to draw a phase line that has one equilibrium point that's a source, there's my equilibrium point. What do I do to make it a source? Arrows away from it, yeah. A node is when one arrow goes towards it and one arrow goes away from it. Okay, so a phase line is another qualitative tool that we can use to study the solutions of an autonomous differential equation. It can only have y's on the right-hand side, otherwise this is a useless tool. But in good news, lots of differential equations are autonomous. So it's good. It's okay to develop tools for just that one kind of equation. All right, so remember that the slope field for an autonomous differential equation has slopes that are all the same along a horizontal line. So if you pick any horizontal line here and look at the slopes, they're all exactly the same. So there's a lot of redundant information in this slope field. Okay, a lot of redundant information. We actually only need to look at a single vertical slice of this slope field, and we will have all the information that the slope field contains. So we're going to compress all this information into a phase line where we mark where dy dt is 0, right? And remember, the places where dy dt is 0, we've been calling those equilibrium solutions. Right, places where dy dt is 0, equilibrium solutions. And on a phase line, we call them equilibrium points, because we're now taking that whole solution and just marking it as a point on the line. Okay, and then instead of marking the exact slope, like a slope field does, where you draw a little tangent line with the exact slope, we're just going to mark whether or not the slope is positive or negative on our phase line. And we're going to indicate it with an arrow. Okay. So we can use the phase line to sketch solutions to the differential equations, but they aren't as accurate as ones we would get by using the slope field or Euler's method, but they give us a good idea of long-run behavior. And I actually was going to make a phase line over here, and I forgot. Okay. So let's do it for this particular problem. So if dy dt is y minus 2 times y plus 1. So first I need to figure out where that is 0. Yeah, so first we find equilibrium solutions, and you get y equals 2 and negative 1. So I'm going to draw a phase line. This is just y. And I'm going to put 2 points on it, negative 1 and 2. And I didn't put any kind of scale or anything, just throw them on there. Now I just have to figure out the slopes below negative 1, in between negative 1 and 2, and bigger than 2. When y is in there, are the slopes positive or negative? Okay, so let's look at y minus 2 times y plus 1. Look at a number line. This might look familiar from Calc 1. So negative 1 and 2 are like fences. Those are places where the derivative is 0. Y plus 1 If you plug in a y that is smaller than -1, is y plus 1 positive or negative? Negative. You can just pick any number, like -10, right? -10 plus 1 is negative number. So all right, what if we put in a number between -1 and 2 into y plus 1? Yeah, pick a number between -1 and 2. Give me a number between -1 and 2. 0. Put 0 into y plus 1. You get a positive number. And then pick a number bigger than 2. Plug it into y plus 1. You get a positive number. All right, so now I'm going to look at my factor of y minus 2. If I plug in a number less than -1 into y minus 2, do I get a positive or a negative? Negative. Pick a number from -1 to 2. Plug it into y minus 2. Positive or negative? Negative. And bigger than 2? Positive. Okay. Then multiply these two things together. Negative times a negative is positive. Positive times a negative is negative. Positive times positive is positive. And this thing, remember, this is dy dt. So below -1, my derivative is positive. So let's go back to the phase line and indicate that. Positive, I'm going to indicate with an upwards pointing arrow. So my derivative below -1 is positive. So I have an upwards pointing arrow. Between -1 and 2, the derivative is negative. So I indicate that with a downward pointing arrow. And then when I'm bigger than 2, the derivative is positive, upward pointing arrow. This is a phase line. So we lose a little bit of information because we don't know the exact size of the slopes like we do in a slope field. But it's so compact and easy to read that it's worth the loss of information. Okay, so here's our phase line. We can use that phase line to sketch solutions y of t. This is just looking at the derivative. I'll put this on a new page. Okay, so here's my phase line. I'm going to use it to sketch some solutions. So this is just tracking derivative. Where is the derivative 0? Where is it positive? Where is it negative? So somebody remind me, if the derivative is 0, what does the solution have to look like if its derivative is 0? So horizontal line, it's a constant. Yeah, so at 2 and at -1, so this is the ty plane. So I'm looking at solutions to the differential equation now. I have a horizontal solution at 2. So there's a solution to my differential equation, equilibrium solution, and at -1. All right, so pick an initial condition, say between -1 and 2. let's say 0, right? Okay. So between -1 and 2, what is the slope? What is the sign of the derivative? Negative. You can tell from this down arrow in the phase plane. Right? The derivative is negative between -1 and 2. Okay, if a function's derivative is negative, what does that tell you about the function itself? It goes down. It's decreasing. Okay, so from here, my function has to decrease. But we know from the uniqueness theorem that it can't cross the equilibrium solution, so it's got to do something like this. And it's always decreasing, so it has to go up in the other direction so that it'll always be going down. And it can't cross the 2 equilibrium solution. But what if I had an initial condition that was, say, down here, like, I don't know, -5 or something? When y is below -1, my derivative is positive, indicated by this up arrow, which means, what do you know about a function that is, whose derivative is positive? Increasing. So from here, my function has to increase, but it can't cross the equilibrium solution. And it has to always be increasing, so it has to be coming from down further. And then if I had an initial condition bigger than 2, okay, when y is bigger than 2, the function is increasing because its derivative is positive, which means it does something like this. And it has to come down on the other side so that it'll always be increasing. So look at how the arrows and how they point to the equilibrium point correspond to how the solutions approach equilibrium solutions, right? So look at the -1. These arrows are pointing towards it. And then when I graph solutions, my solutions come towards the equilibrium from both sides. And with my 2, the arrows are both pointing away from it. And when I sketched solutions, my solutions both went away from the equilibrium solution when you're reading left to right. Does that kind of make sense? Okay. So the uniqueness theorem was important here in sketching those solutions because we have to be able to know that we can't cross equilibrium solutions. Okay, so this is a good qualitative picture. We know what happens in the long run. Like if I wanted to know y of 5, that might be a hard question. But if I want to know the limiting behavior, what happens to this differential equation in the long run, it depends on the initial condition, right? If you start below -1 or between -1 and 2, the differential equation is going to approach -1. Its solution is going to approach -1. If you start bigger than 2, it's going to go off to infinity. So equilibrium points can be classified as a sink, a source, or a node. Sink is when everything goes towards an equilibrium solution. So in this case, -1 is a sink. Both the arrows point towards it, and when you sketch solutions, the solutions both approach it from either side. And 2 is what we call a source. The arrows on either side in the phase line point away, and when you sketch solutions, the solutions leave the equilibrium solution. Yeah, if one's pointing towards and one's pointing away, we call that a node. So let's see, if I had one arrow pointing away and one arrow pointing towards, something like that. If I were to sketch a solution of that thing, let's say here's my equilibrium solution. If I pick any initial value below there, below the equilibrium solution, my derivative is positive, right? Which means the function has to be increasing. So it's going to approach the equilibrium. Maybe it's going to have to do something like that on the other side because it's always increasing. If it's what? Oh, I see your question. Yeah. How could the slope be 0 if it's not going from positive to negative? Can anybody think of a function whose derivative is 0 at a point, but the slope doesn't change sign. Yep. So y equals x cubed. So back to Calc 1, nothing to do with differential equations, right? When you sketch y equals x cubed, and you look at tangent lines, we've got positive slopes. I drew this very badly. There's a horizontal tangent line at 0, and then the slopes are positive again. Okay, so if I am on the other side of my equilibrium solution, I'm above the equilibrium solution, my derivative is positive, which means that the function is increasing, which means it's going away from my equilibrium solution. So this guy is a node. It's neither a sink nor a source because the solutions tend towards it from one side, but away from it from the other. So this is what we call a node. And then up here, I'll write sink and source. Okay, some for you to try.